Okay guys, so today we are gonna be doing something special, like really special. So a friend of mine left our country quite some time ago to go abroad and study in Norway. And well, since she has just begun her journey through the beautiful world of calculus, I thought, I might give her a little bit of help. I will maybe record something that would tell her something about Calc 2, some double integration. Let's say. So we would like to solve this beautiful double integral from 0 to 3 and from negative square root of 9 minus x squared to the square root of 9 plus x squared of x cubed plus x times y squared dy dx. And so, well, you see, I would like to kind of make this an explanation because this all the time ago when we used to go to the same school, stuff like this, I would kind of sit with her on the corridor and show her some fun math stuff like this. And so I'm just gonna be explaining to you as I would be explaining it to her if she was right here next to me. So we would like to solve this double integral. So first of all, what does this integral even mean? Well, we would like to interpret this whole stuff like this as integrating a 3D function over a defined region on the 2D plane, yes, so on the xy plane. And this region would basically look something like this. We are given Cartesian coordinates, yeah, so this is gonna be the floor on which we place the graph that we want to take the volume under which, yeah, and this is gonna be the region that we're gonna be calculating this volume on, yeah. So, well, this thing right here is just y calculated as if x and y created a circle of radius 3, yeah. So this is exactly the same thing as saying that y squared plus x squared is equal to 9, yeah, so 3 squared. And so we see that what we actually want to do here is create a circle with radius 3, send it at the origin. Oh, it's not quite centered. Yeah, now it's a little bit better. Oh no, now it's awesome. So it's gonna be the circle of radius 3. It's not 0, it's negative 3. And we know that x goes from 0 to 3. So we only care about those values of x in blue right over here. And we know that y goes from negative square root of 9 minus x squared, so this stuff, yeah, to positive this square root, yeah, so this stuff. But since we only care about those values of x, we only care about, about those values, those values of y, and so we only care about this region here in total, yeah. And so we would like to calculate the volume under the curve of this function x cubed plus xy squared defined, under on an area defined by this region right over here. Yeah, lovely. Well, doing this one kind of straightforwardly, so just taking the integral of all the stuff that we have here inside with respect to y and then plugging in those square roots and stuff like this, and then taking another integral from 0 to 3 of all those expressions in terms of x, like that would be a mess, yeah. Just being honest here, because even though we have y squared here and those square roots would definitely cancel each other out, but then we would have all that multiplication stuff. I don't want to do that. It's gonna be just messy. I would like to show you a beautiful approach here. So whenever we are integrating something on a circular region, yes, on a region where kind of wherever we look, sending at the origin, we are seeing kind of the same thing, yeah. So we have this nice circular symmetry there. We can actually convert it into polar coordinates. And well, what the hell are polar coordinates? Well, let me explain. So if I were to draw myself the regular Cartesian coordinates that we all just use in school, and they would look something like this. I would have my y-axis, I would have my x-axis, yeah. And now if I were to make a point, I would like to draw a point somewhere, let's say this point 1, 1. Then what I'm doing by defining this point is I'm actually defining a an instruction on how to get to that point. Yeah, so this instruction is, well, go by 1 to the right. Yeah, you probably can't really see it's yellow. Yeah, so go by 1 to the right and then go by 1 upwards. Yeah, but if I were to, well, mark this exact same point with the exact same distance from the origin, with actually the same exact position, yeah, with respect to the origin as here, but in the polar coordinates, yeah, so I've got something like this. Those are gonna be my polar coordinates. I'm just drawing this second axis here for the reference. Yeah, this is gonna be my r-axis. I would draw it here and I would call it the square root of 2 and pi over 4. Well, I'm actually giving just a little bit of a change instruction here. So the instruction I'm giving now is go by a square root of 2 in the positive r, or positive x direction, and then rotate this segment, this line segment, of the length square root of 2 by an angle theta, which in this case is equal to pi over 4. And well, doing those two operations, yes, so performing those two operations, going from the origin by 1 to the right and then 1 up, or being at the origin, going by square root of 2 to the right and then rotating that line segment by a pi over 4 counterclockwise from the positive x-axis, yes, so from the horizontal axis, let's say, just forget about those x's and stuff. Well, those are two exact same points. And now a nice thing is that here I can actually pretty nicely convert my polar coordinates to my regular Cartesian coordinates. And why is it so? You see, here in the Cartesian coordinates, I go by 1 to the right and then 1 up. Yeah, and I could actually do the same thing here in the polar coordinates. Yeah, so I could just say that I'm going by 1 to the right. Yes, I'm going by some value of x to the right. Yeah, but well, what is this value of x? You see, I'm given this angle theta and I'm giving this, I really hope it's called the adjacent. No, it's hypotenuse? Shit, man. Whatever. This third side of the right angle triangle. Yeah, so I can actually use trigonometry to calculate the length of this line segment. That's gonna be the r times cosine of theta, where r is this square root of 2 segment right there, and theta is this angle between this line segment of length r and the horizontal axis. And just as well, I can calculate the length of this line segment right over here. It's just gonna be by trigonometry r sine of theta. And so I'm getting pretty lovely so-called conversion formulas that I use to convert from polar coordinates to Cartesian coordinates, from Cartesian coordinates to polar coordinates. Yeah, so that x, yeah, so by how much I move in the positive x direction is gonna be just r multiplied by the cosine of theta. At the same time, how much I move upwards is gonna be defined by, in the Cartesian coordinates by y, but here by r multiplied by sine of theta. So just a quick recap. So what we did here is, just so you know, here in those polar coordinates, we define points, yeah, by specifying two values, which is first of all the r, which kind of stands for radius, yeah, which is by how far we go in the positive direction on the horizontal axis, or how much or how much we can go to the negative side, but well, how you prefer it, yeah. And then we have the second component, which is the angle theta, by which we rotate that line segment just created of the length r, counterclockwise from the horizontal axis. Yeah, awesome. So r and then the angle theta. Yeah, those are our polar coordinates. And well, now, yeah, we would like to integrate stuff using those polar coordinates, but the problem is that, well, we would really need, if we have, to integrate, we would need to know by how much does an area in this polar coordinate system change when we are changing r and theta. Because, well, in the Cartesian coordinates is kind of straightforward. Yeah, we've got our height of that rectangle when we doing integrals, and we've got this width, which is just the change in x, all that stuff. And so we can quite nicely calculate the change in area just, using some basic geometry. But here is a little bit more complicated. And I mean, it's still just basic geometry, but a little bit more complicated. So let's try and see, well, what's gonna be the change in area in this whole polar coordinate system. Yeah, so let's say I'm gonna have some area. Yeah, so this is gonna be my area, and this region right here was the original area, and this guy right there is gonna be my change in area, the delta A, which is what just stands for the change in the area. Yeah, so that's gonna be my wedge, and here I'm gonna say that my angle theta changed by some delta theta. Yeah, so this is gonna be the it kind of looks like I'm creating the third region here, but no, it's just the angle. So maybe I'm gonna denote it in some different color, let's say in yellow. Yeah, so that's gonna be my delta theta, like this right here. Okay, and now I also have to specify my delta I, so the change in the radius in this coordinate of my points in the polar coordinates. And well, this is gonna be just this thing is gonna be my change in R. Awesome. And so how am I supposed to define this area here? I mean, it's not quite a rectangle. You see it has those rounded sides there, so we can't really use any kind of like a real basic geometry. However, well, there's a nice trick to do this thing. I would like to define my change in areas, yeah, so my delta area as. And I would like to take this entire huge area, this, like big area, so maybe I will denote the big area right there as BS. Yes, so that's gonna be big area. Big. Yeah, that's gonna be BA, big area. That's how we say area in English. Yeah, so areas that starts with an A. Lovely. That's gonna be my big area, so BA minus, and I would like to subtract my small area. That's gonna be only this original stuff right there. Yeah, so it's gonna be my small area. So it's gonna be minus my SA. Lovely. So now, what is the big area? And I would like to introduce a nice trick there. First of all, I have to get rid of those lines because they are kind of screwing up my view, but yeah, let's just stick with it. Okay, so I would like to create myself some new radius. I'm gonna call it, let's say, R sub k. And R sub k is gonna cease in proceeding further just here in the middle of this wedge. Yeah, so it's gonna actually, so those two segments are gonna be of equal length. They're gonna be E of length delta R over 2. Yeah, so delta R over 2, both of them. And so now, after doing this thing, we can actually go on and say that the area BA, yeah, so the big area is gonna be equal to what? Well, that's gonna be equal to this thing would have been a circle, yeah? So we have to do pi times the radius of the circle squared. So it's gonna be pi, but what is the radius of this circle? Yeah, so the circle that would have normally created this guy, sorry, this area right over here. Well, that would be just our R sub k minus this delta R over 2 right over here, yeah? So that's gonna be just this R over there. So that's gonna be our R. Oh no, why am I creating another parenthesis? R sub k, and then minus. No, wait. That's a small area. plus this thing right there. So I would like this line, this blue line right there. That's gonna be my plus delta R all over 2 everything squared. But remember, we are not taking the area of the entire circle, but just a segment created by this tiny notch in theta. So we still have to multiply this thing by, well, properties of how we define area in a segment defined by some angle, by the angle itself. So delta theta, the change in theta all over 2 times pi. So those pi's are gonna cancel each other out nicely, but let's just leave it for now. And now the small area, so this is exactly what I started to do earlier, but let's just forget about it, so we would like to get this radius right here and do exact same thing. So our small area is going to be equal to pi multiplied by r sub k plus, now minus the delta r all over 2. That's going to be the radius. I'm going to square it. I'm going to multiply it by pi. And once again, we're only taking a nudge of it, not the entire circle, but just a slice of it, defined by the angle theta. So we have to, by the angle delta theta, so we have to multiply by the change in theta all over 2 times pi. And so now what we get is that our change in area, this delta area right here, I'm gonna maybe slide it down here, is gonna be equal to just cancelling out those pi's, taking out the delta theta out, and then we have this r sub k minus delta r over 2 squared, and then minus r sub k, plus, and now minus delta r over 2 squared. And when you go on and just calculate everything out and do mess around with this awful trigonometry, you're gonna end up with delta A being equal to r multiplied by dr by delta r times delta theta. And so now what we see is that, well, given this thing right there, we will have this change in area given by r multiplied by delta r multiplied by delta theta. And so our regular change in the area given by dx and dy, so the change in x multiplied by the change in y is gonna change, so our dx dy is gonna change into r multiplied by dr multiplied by d theta, so the slight change in x multiplied by the slight change in y is gonna change into, well, just r multiplied by the slight change in r multiplied by the slight change in theta. And that's exactly what we were after here. So, well, now we are actually perfectly ready to go on and convert our original integral into polar coordinates. So let's go on and do it. We would like to convert this integral, so this integral from 0 to 3, this negative square root, positive square root of x cubed plus xy squared dy dx. So that's gonna be, maybe I will just rewrite it, 0 to 3, negative 9 minus x squared, positive 9 minus x squared, x cubed plus y squared x, and now everything dy dx. Lovely. And so now, well, first of all, we know that we are supposed to integrate over this region. How do we define this region in polar coordinates? So if I were to define this region right here using only the value of r, which is by how much I move from the origin to either one of sides, and by the angle theta by which I rotate this line segment given by my transition, by my walk from the origin, I would get, well, this angle here is just 90 degrees, is pi over 2. The angle there is negative 90 degrees, is negative pi over 2, and the radius is the maximal radius is 3 and the minimal radius is 0. So my r is going from 0 to 3 and my theta is gonna go from negative pi over 2 to pi over 2, and that's gonna define my beautiful region right over there. So lovely. I have my bounds for integration. That's lovely. So let's start. First of all, I have my theta values, so negative pi over 2 up to pi over 2, and then the integral from 0 to 3, those are going to be the bounds of integration for the r. And now, how do we convert x cubed and y squared x into polar coordinates? Well, we know that x is equal to r cosine of theta and that y is equal to r sine of theta. and by, well, what we achieved through some trigonometry right over here. So we can just kind of go on and use those formulas in order to convert our x cubed and y squared x into polar coordinates. So that's going to give us, just kind of factoring the r cubed term, and then here we're gonna get, well, this x squared is gonna consist of a cosine cubed, actually. Oh, maybe, you know what, I'm just gonna take out the x first of all. So that's gonna give me r multiplied by cosine theta, and then r cubed cosine theta, and here inside I would get cosine of theta that was left from those x's, and then plus a sine squared of theta that was left from the y squared. And so I can just say it's all equal to a 1 because of, well, trigonometry identities, like the trigonometric one, I think that's how it's called. And now we just have to go on and apply our change in area. So r dr d theta, notice that this r here is the same as those are there, so just we're gonna have to multiply this entire thing through. Now simplifying this stuff a bit will give us the integral from negative pi over 2 up to pi over 2 of the integral from 0 to 3, that's an awfully long integral, from 0 to 3 of r to the 4 cosine of theta dr d theta. But, well, this thing's nothing but, well, easy. We can just go on and take the antiderivative of r to the 4th power cosine of theta with respect to r. Cosine of theta is just going to be a constant with respect to r, and so we will get that this entire thing is equal to the integral from negative pi over 2 up to pi over 2 of, now it's going to be cosine of theta multiplied by r to the 5th over 5, all in the bounds of 0 and a 3d theta. But, well, this thing's just going to be, well, 233, so 3 to the power of 5 all over 5 minus a 0 on the lower bound of this integration, it will just be a 0. So this thing is going to be equal to the integral as theta goes from pi over negative pi over 2 up to pi over 2 of 243 over 5 over 5 of the cosine of theta d theta, but this thing is just nothing else but 243 all over 5 multiplied by sine of theta, all evaluated between negative pi over 2 and pi over 2. We know that. Okay, guys, so I got kind of cut there because my camera died, but we don't really care about it. We are moving forward, and so, well, we're actually at the very end of this video, so, well, let's just not care about it. So that's just gonna give us, because sine of theta is equal to a 1 and a negative 1 on the pi over 2 is gonna just give us the nice 268 all over 5, which is lovely. So thank you guys for watching. I hope that my friend was watching this video. If you did, well, also thank you for watching. Okay, so I hope to see you next one. Bye.